Today on Macaulay Math, logarithms, my favorite. Intro. Okay, good day. I'm Professor Macaulay. This is Math 150 Pre-Calculus, Lesson 12 on logarithms and logarithmic functions. Our goals for today: we're going to recognize and evaluate logarithmic functions of base A. We're going to graph logarithmic functions. We're going to recognize and evaluate logarithmic functions of base E. And then we're going to use logarithmic functions to model data and solve problems. Logarithmic functions are often used in the world to represent large variations of values on a manageable scale. For instance, the decibel and pH scale are both examples of logarithmic scales. Logarithms are also used to solve equations when the variable is an exponent. In this lesson, logarithmic functions will be introduced as well as some of the elementary properties of logarithms. Okay, so let's start with the definition. And this expression right here is read log base A of x equals y. That's how you read this. And log base A of x equals y if and only if a to the y is equal to x. Now this definition is literally just a reorganization of variables in a way that takes a exponential expression and converts it into a logarithmic expression. And what I mean by that is that the base of the logarithm, that a there, becomes the base of the exponential, that a there. The value of the exponent, this y right here, becomes what the logarithm is equal to. And this value x that we are taking the logarithm of becomes what the exponential, after you've calculated it, is equal to. It is literally that simple. It is just moving the variables. Now, once we determine that definition, we can come up with some very simple properties that we will use quite extensively. All of these simple properties of logarithms are based solely on that definition. They are converting from logarithmic form to exponential form. Log base A of 1 is equal to 0 because if I take the base of the logarithm and I make it the base of the exponent, and I take what the logarithm is equal to and I make it the exponent, well, clearly anything to the 0 power is 1 as long as a is not equal to 0. Similarly, log base A of a is equal to 1 because I take the base of the logarithm a and I make it the base of the exponent. I take this 1, the value of the logarithm, and make it an exponent. Clearly, a to the first is just equal to a. That's a normal exponential and variable convention that we know. Additionally, if I go log base a of x to the a, if you have the logarithm with a base and an exponential with the same base, then the value of that, there's more to it than this, but for all intents and purposes, the a's and the logarithms cancel out and you get just x. Similarly, if you switch them and have a logarithm as an exponent, the logarithm and the exponent will cancel out provided that the bases are the same. And then finally, if you have two logarithms with the same base that are equal to each other, whatever expression is inside the logarithm must also be equal to each other. Let's talk about graphs. First, here I have two generalized exponential and logarithmic graphs. In the generalized exponential function, if there is no value in front, when you plug in 0, anything to the 0 power, you get 1. So a simple exponential function will always go through this 0, 1. Since a logarithm is an inverse, whenever you have an inverse, you switch your x and your y, and we can see that in this logarithmic function, we also have a corresponding point where the x and the y have been switched from the coordinates in the generalized exponential function. We also know that in a generalized exponential function, the domain of the generalized exponential function is all real numbers, and the range is just
values of y that are greater than 0. In a logarithmic function, the domain and the range have been switched. The domain of a logarithmic equation is just values of x that are greater than 0, and the range of a logarithmic function is all real numbers. We can see that fairly easily in a Desmos demonstration. Here I have two simple exponential and logarithmic functions. I have f of x equals 2 to the x, that's a simple exponential function, and I have g of x equals log base 2 of x. I have used f of x to determine 2 points. I said a, and a is just a slider currently equal to 1, and then f of a. So this point 1, 2, when I plug 1 into this function, 2 to the first gives me 2, and then I switch the x and the y from the purple point to f of a in the black point. And you'll notice that it immediately lines up on this logarithmic function. So when I do move this slider, let's say I move it to 2, you'll notice that again I have 2, 4, and then on the logarithmic I have 4, 2. This isn't a proof, but it gives you a good intuition that as I slide along, you'll notice that the x's and the y's have been switched. It gives you a good intuition that this f of x function and this g of x function are in fact inverses. We also see that the domain of the general exponential function is all real numbers, and the range is y is greater than 0. And then the domain of the logarithmic function is x is greater than 0, and the range is all real numbers. Now, there are two logarithms that you will see used quite a bit, more than other bases. Most scientific calculators include these logarithms with known bases, and Desmos is no different. You can type in ln and you can type in log, and Desmos will use those. Desmos is a little bit more powerful than most handheld calculators in the fact that it's fairly easy to put in any base that you want. That being said, the natural logarithm is going to be y equals ln x, and so whenever you see this ln x, it is a logarithm. It is specifically log base e, where e is Euler's number that we learned in the last lesson. Common logarithm, if there is no value listed beneath, just like when we see a as a variable, we know as an exponent there's a 1 there. Just like when we see the square root of 2, we know that that is a 2 in that little trough. Whenever you see nothing for a logarithm, you assume that it is log base 10. Why is log base 10 important? Well, our number system is base 10, and every time you go over a place, you go up by a power of 10. So that's going to be very useful. Finally, before we get into examples, let's talk about why we're learning logarithms in the first place. Now, I'm making an assumption here, but I'm assuming that if you are watching this video to learn pre-calculus, you can probably solve this thing in your head. You can say, okay, I have 9 equals 3 to the x, and I have to ask myself, 3 to what power is equal to 9? Well, that's not too difficult because we know that 3 squared is equal to 9. The problem lies when we get to something that's more like this. If I have 10 is equal to 3 to the x, there is no whole number that when you take 3 raised to that whole number, you'll get 10. We know that 3 squared is 9, and we know that 3 to the third is 27. There's no whole number value that I can raise 3 to get 10. So I'd have to estimate. We can say that it has to be somewhere between 2 and 3, probably closer to 2 than to 3, but we can't get any real accuracy for it. We can use logarithms in a calculator to get a solution to this accurate to as many places as you would like. Now, we're not going to do that today, but that is going to be our ultimate goal. Let's talk some examples. First example, convert log base 2 of 32 to the 5th to exponential form. So when they're asking us to convert, all we're really doing is we're using this definition that we learned at the beginning, and the base of the logarithm becomes the base of the exponent. What the logarithm is equal to becomes the exponent of the exponential, and what you're taking the logarithm of becomes the value of the exponential. So I can just take this logarithm that I have written here. The base of the logarithm becomes the base of the exponent. What the logarithm is equal to becomes the exponent. And what you're taking the logarithm of becomes the value of the exponential. Similarly, when they ask us to convert from exponential to logarithmic form, we just reverse the process. The base of the exponential becomes the base of the logarithm. The value of the exponential becomes what you are taking the logarithm of, and the exponent of the exponential becomes the value of the logarithm. It says use the definition and properties of logarithms to solve. So we have something like this: log base 3 of 3 to the negative fifth. And if you have logarithms and then exponentials all with the same base, in this case it's 3, usually something is going to cancel out. And so when I look at this one right here, I come down and I see in property number 3 that log base a of a is equal to x. So if I have a logarithm that has the same base of an exponential, then whatever that exponent is the value of the logarithm. So when I come back down, I can say that for all intents and purposes, the logarithm and the 3's cancel, leaving me with negative 5 is equal to x. And I can't simplify that any further. So that's a pretty easy example. Here it says describe the transformations from the function f to g. And so in g, I see log base 8 of x as my parent function. And in this, I see two transformations. I see this plus 4, and then I see this minus 1. And so when I list my transformations, I'm going to want to list them as if I were evaluating. Now, logarithms are inverses of exponents, so they are on the same level in the order of operations. Just like addition and subtraction and multiplication and division are on the same levels for their order of operations. So if I pick a value, let's say I pick 5 for x, and I plug in, what is the first thing that's going to happen? Well, I'm going to subtract 1. So if I'm subtracting 1 from the variable, then that is going to be a translation 1 unit right. After I have subtracted 1, then I will take the logarithm, that is the function, and then I will add 4. So if I'm doing anything after the function, I'm doing it to the y values. So this says add 4 to the y values, which will be a translation 4 units up. And we can check that using Desmos. So here I have both f of x and g of x graphed. And that general point 0, 1 on the original graph, which is going to be on all simple logarithms, has been translated up to 2, 4, which is 1 unit right and 4 units up. So I feel very confident from this diagram that we have the correct answer. Next example, use properties of logarithms to simplify the following. Negative ln e. So solving this is going to lead us to a result that's going to be very useful for us as we go forward. So I definitely want you to put this part in your long-term memory. But ln e, if you remember, ln is just log base e of e. Now, what do I get when I have log base of the same value of what we're taking the logarithm of? Well, if we go back to that list of properties, if I have log base a of a is equal to 1, and so we can say that we still have to have this negative, and this log base e of e is just 1, so I get negative 1. But the real takeaway, the most important part from this that you can take away, is that the ln of e is always going to be equal to 1. Please put that in your long-term memory. Here we have e to the ln of 22, and if we remember that ln is again log base e, and you don't always have to write that step of 22, we can go back to those properties that we had, and we can say, all right, if I have e to the log base e of x, I'll just get x. So here, since I have e to the log base e of 22, I'll just get 22. And then in this last one, we'll do something similar, but the first thing I want you to do is I want you to recall that a to the negative x is equal to 1 over a to the positive x. So I can rewrite this as log base e of e to the negative 4. And then if we go up and take a look at our examples, again, if you have log base e of e to the x, you'll just get that x. So for all intents and purposes, in this example, the log and the two e's cancel out, leaving us with just negative 4. Well, that's all I have for today, folks. So, the Star Wars fun fact of the day: if Carrie Fisher had not been able to play Princess Leia, George Lucas's second choice was to be Jodie Foster of Silence of the Lambs fame. It would have been a different movie. Well, that's all I have for today, folks. Have a great day. Goodbye.